Hello, everybody. I hope everybody is doing well. So, this is me, and I again welcome you in lecture number 4 of chapter Light. So, let's move on to the next slide and let's try to understand what is there for us. So, here we will be discussing the images formed by the convex mirror. In the previous parts, we had already seen the images formed by the concave mirror. Now, here the rules and the phenomena is also same as we have discussed in the case of concave mirror. Here also we will form the images by the help of rules, by the help of rules which we have seen in the previous lectures. So, what is our motive? So, our motive is to find out the position of the image, when we place the object at different locations. So to find out the position of the image at different position of objects. So this is our motive, and because we have a very clear idea about the rules of image formation, so we can simply do that. Okay, now guys, this is a convex mirror. Now why it is a convex mirror? It is very simple, because here in this case the light is being reflected from this part of the mirror. This is the outer part or the outer surface. So by this outer surface, the rays is being reflected. That's why this is a convex mirror. This is a convex mirror. Okay. So now let's talk about the position of an object. So here I have placed the object at infinite distance from this mirror. Now you might be thinking that how can we place an object at infinite distance? So for your simplicity, I want to let you know that here the distance between this concave mirror and this object is very high. It means it has been placed far away from this concave mirror. That's why it has been written at infinite distance. So here the distance between this concave mirror and the object is assumed to be infinite because it is far away from this mirror. Now guys, let's talk about the position. So to find out the position of the image, we have to draw the ray diagram. So let's suppose this is our object and this is a ray coming parallel to this principal axis. This is principal axis, and this ray is coming parallel to this axis. Now after the reflection, or after hitting the surface of this convex mirror, this will be reflected like this, and this will be going like this, and it will appear to pass through this point F, because if you move this ray behind the mirror like this, then it will be appearing to be passing through this point F, and this is a focus of the convex mirror. In the case of concave mirror, the focus, remember, the focus used to be here at the same side of the mirror, but here the focus is behind the mirror. So this is the difference between the concave mirror and a convex mirror. Let me write it here for you. Focus of a convex mirror is behind the mirror. Okay, I hope you got my point. Now, what is the position of an image? So this ray is appearing to be coming from this point F, and this ray will also be appearing to be coming from this point F. Now, they will be appearing to be meeting or crossing each other at this point F. And what I had told you that where the rays meet, our image is formed there. So here, in this case, the image is formed at this point F. Okay. So now, let's talk about the nature of the image. Let's talk about the nature of the image. So nature of the image is that because rays are not actually meeting here. At this point, you can observe that rays are not actually meeting. They are appearing to be meeting. That's why the nature of the image is virtual. It is a virtual image. You cannot obtain it on a screen. That's why it is virtual. Now, I had already told you that virtual images are always erect. Virtual images are always erect. Real images, real images are always inverted, and virtual images are always erect. So this is a virtual image. That's why it will also be erect. It means upright. Erect means upright. I can write it here. Erect means upright images, as you can see in the case of plane mirror. Now, guys, let's talk about the location or the position of the image. So, by the help of this diagram, you can easily understand that the image is formed behind the mirror at this point F. So, you can simply write behind the mirror at point F. But in the case of concave mirror, remember that point. At that time, we were getting the image at the same side. But in this case, the image is behind the mirror. Okay, and in that case, the image was real and inverted. But here we are finding the image virtual and erect. Now, guys, let's talk about and let's comment on the size of the image. Size of the image. Size of the image. So as you can see in this image, that this is a point size image, and it is very, very small. And for small, we write diminished. For small images, what do we call small images? Diminished. So in this case, the image is highly diminished. It is very, very diminished image. So I hope all 3 points we have known for this case. If you place the object at infinite distance, we have found out the nature of the image, we had found out the location or the position of the image, and also the size of the image we had figured out. Now, guys, let's move on to the next slide. Let's talk about the second case. Okay, so here, this is the second case. In the case of concave mirror, we had seen six cases. Six cases in the case of concave mirror. But if I talk about the convex mirror, then you have to just remember two cases. This is as simple. Okay, just two cases is to be remembered. But in the case of concave mirror, it was a little bit difficult to remember. You have to have a very good understanding of the ray diagrams. Ray diagrams are very, very important. So guys, in this case, what will happen? This is a convex mirror. This is focus F, focus. This is a center. Okay, so let me write it here for you. This is center. This is point P, and P stands for pole. Okay, now we had placed this object anywhere before the mirror. Okay, like I'm not actually determining or I hadn't fixed the distance. It can be anywhere, but it is the same size as the mirror. So it can be anywhere. So in the previous case, we had placed the object at infinite distance, but now it is not at infinite, but it can be anywhere. So now what will happen? This is a ray coming parallel to the principal axis. After the reflection, it will diverge like this. It is because it is a diverging mirror. Convex mirror is also known as a diverging mirror. I'm writing it here for you. Convex mirror is diverging mirror. Diverging mirror. And concave mirror. Concave mirror is a converging mirror because it converges the rays. And this is, and if I talk about the convex mirror, then it diverges the rays. So it will diverge rays like this. So this appears to be coming from this point F because this is parallel. So if a line is parallel or if a ray is parallel to the principal axis, then it is appear to be coming from this point or to be passing from this point F. Now there is another ray which is appearing to be passing from the center of convex mirror. This is center of convex mirror. So this ray is appearing to be passing from the center of the convex mirror. And I had told you that whenever a ray appears or actually pass through the center, then it follows the same path and it will again going in the direction of the center. So it will again appearing to be going or to be passing from the center field. So if I increase or if I move this ray behind the mirror, then this will be appearing to be passing from the center C. And this is the point where these two rays are meeting. This is the point where these two rays are meeting. You can simply observe it by the help of this diagram. This is the point where these rays are meeting. So now we can simply say then our image is formed between this point P and F. So our image will be formed between pole and focus. So here the location of the image is behind the mirror and between P and F. Okay. Now let's talk about the nature of the image. Let's talk about the nature of the image. The nature of the image is virtual and erect. Virtual and erect. Now I think I do not need to again tell you or again explain this concept that why this is virtual, because it is very simple. It can be shown very explicitly that the rays are not actually meeting here. They are appearing to be meeting at this point. So that's why the nature of the image is virtual, and virtual images are always erect. Even you can see it. Even you can see this, that here the image is upright. So that's why it is erect. Okay. Now one more point is yet to be discussed, and that is the size. So what is the size of the image? This is point number first. This is point number second, and third point is size. So you can simply see that here the object is larger than the image. So that's why the size of the object is diminished. Diminished means small. Okay. So I hope you got my points. So these 3 points we have discussed for this second case. So here the cases are over. These are just 2 cases in the case of convex mirror. But when we have to study concave mirror, then we have to study 6 cases. So for your simplicity, let's move on to the next slide. And I have cut it short so that you can remember before the exam. You can just simply see this table and you will realize all the cases which we have discussed in the convex mirror. So, position of the image. So, image will form, sorry, this is the position of the object. So, image has been placed at infinity, but the image is formed at focus. Image is formed at focus and behind the mirror. Now, in the second case, we have placed the object between infinite and the pole. It can be anywhere between infinite and the pole. Then the image will be formed between P and F. Between P and F. And it will also be behind the mirror. That's going to be previous slide, and you can see it is behind the mirror. And in first case, when we have placed the object at infinite distance, even in this case, you can see that the image is behind the mirror and at point F. So, if I talk about the size, then in first case, the image was highly diminished. It was a point size image. You can see here, it is a point size image. But in this case, the image is diminished. It is not point size, but it is also diminished. It is smaller than the object. Now let's talk about the nature of the image. It is very, very crucial term, nature of the image. In the upcoming, parts, we will be solving some numericals also. Even in this part, we will solve some numerical. So at that time, this nature of the image is asked very frequently in the questions. So you have to. I will also tell you how to calculate nature of the image. So for now on, just remember that in case of a convex mirror, the image is always formed virtual and erect. Okay, so the images formed by the convex mirror are always virtual and virtual images are always erect. So I hope guys you got my point. Now let's move on to the next slide and let's talk about the uses of convex mirror. So basically, before telling you or before discussing the uses of convex mirror, I want you to know that you can observe this thing that in the case of convex mirror, the size of the image is always smaller than the object. It is very small as compared to the actual size. Okay? And in this case, when you place it at infinity, it is very, very small. So that's why we can use this mirror when we have covered a large area. When we have to cover a large area, we can use this mirror because the images are small here and more and in the same space it can cover more objects. So it is used in the rear sides of car. So at rear sides of car we use convex mirror. And now you might get why do we use it in the mirrors of or the rear side mirrors of car? Because it can cover a larger area. A larger area can be seen in a small size of mirror. Now in the case of device to check theft in shop, you might have seen this in a shop. In a shop, these type of convex mirrors are placed so that we can easily detect the thief. Okay, because it covers the larger area. So wherever we need to see a large area or wherever we need to see the small size images of a larger object, small size images of a larger object, then we use convex mirror. Okay, I hope you got it. Now let's move on to the next slide. Okay, so now the conceptual part or the theoretical part of this chapter light has been finished. Now we are moving ahead to solve some numericals. And to solve those numericals, we have to have a very clear understanding of these Cartesian sign conventions, because in later parts we will be applying some formulas, and in our formula we have to put value with sign convention, with sign convention. So if you put a wrong value, okay, if you don't apply the sign convention, then your answer will be wrong. So you have to be very carefully. You will have to pay all your attention to this sign convention part. So if a object is placed left to the mirror and the pole is taken as the origin. So for an example, let me tell you a very simple thing. Let's suppose this is a graph. This is a graph. In our mathematics, we frequently use graph. This is a graph. This is x-axis. This is y-axis. Okay, this is minus x. This is minus y. So the distances which are at this side are taken positive, and the distances at this side are taken negative, and the distances on the upper side are taken positive. This side positive, and this side is taken negative. Negative. So the same phenomena or the same thing happens with a mirrors also. For an example, this is the mirror. So the distances from this side. Let's suppose this is our origin. Okay, this is our origin, and the distances from right side are taken to be positive. Are taken to be positive. Okay, let me write sign convention a little bit more clear. Okay, so the distances this side are taken positive, and the distances which are left side are taken negative. Negative. And the upper distances are taken positive. For example, this is the height of the object. So I will write it positive. Let's suppose the height of the object in this case is 4. And because it is upper, then I would say the height of the object is 4 centimeters. But if had I made this like this, and I made this line like this, in this case, the height is, let's suppose, 4, but I will write it minus 2 centimeters. Why? Because this is the lower side of this mirror. This is the lower side of this principal axis. So that's why I will take it as minus 4 centimeters. Okay? And let's suppose the distance of this object from this mirror is 5 centimeters. Then I will write it, whenever we solve the question, I will write it minus 5. Okay? Why? Because so we have taken it minus 5, minus 5 because it is at the left side of this mirror. So that's why we take it as minus 5. Okay? Had it been here at this side, that this would have been in positive. So I hope guys you might have got it that what is the Cartesian sign convention. This is very, very important. Now, whenever you use it in formula, then you will have a clear understanding. In the last part of this lecture, I will be solving a numerical also, so you will more understand what I am talking about. So let's move on to the next slide, and let's try to understand. Here, the same thing is written. The distances to the right of the origin is positive. Right of the origin is positive, while that to its left is negative. And that distances which are left side are negative. Okay, we already know it. Now the third point is distances above the principal axis, positive y-axis you can say are positive, while those below it are negative. Okay, or the negative y-axis. So this is the distance lower the principal axis or below the principal axis. That's why it is negative, and this is positive. Now, guys, this is the formula which is frequently used to solve a numerical. Okay, and this formula is known as the mirror formula. This is a mirror formula for spherical mirrors. So this formula is 1 upon V, 1 upon V, and V refers the image distance and U refers the object distance and F refers to the focal length. Okay, and you are already familiar to these terms. I don't need to explain you again what is focus, what is object distance and what is image distance. So now let's talk about the sign convention in the case of convex and concave mirror. So for your simplicity, I am drawing a diagram of a concave and a convex mirror. This is your concave mirror because the coating is in outer side and the light will be reflected from the inner surface. And this is your convex mirror because the coating is at inner side, and the light will be reflected from this outer surface. This is your convex mirror and this is concave mirror. Now, in the case of concave mirror, the object will always be here because light will reflect from this side. So that's why the object will be placed always here. So that's why the object distance will always be taken in negative in the case of concave mirror. But if I talk about, sorry, this is a concave mirror. So I will be placing an object here. So that's why it is negative. Now, in the case of convex mirror, let me draw it here. This side. Okay. So let's suppose this is our convex mirror. So here also the object will be here at negative side. So that's why the object distance is negative in the case of both the mirrors, convex mirror as well as concave mirror. Now let's talk about the image distance. So you might have seen that in concave mirror, the image was formed at the same side because the rays were actually meeting. So that's why till 5 cases, because we had discussed 6 cases of a concave mirror. So till 5 cases, the image was formed at the left side. So that's why for 5 cases, the image distance will be negative. The image distance will be negative. But in the last case, or you can say 6th case, what happens? The image was formed behind the mirror. So for 6th case, we will take the image distance as positive because in 6th case, you can observe or you could have seen, or you can simply see the last lecture and you can observe that the image was formed behind the mirror in 6th case. So that's why the image distance is taken positive for those cases. Now, let's talk about the image distance in case of convex. So in the case of convex, the image was always formed behind the mirror in both cases. In one case, the image was formed at F, and another case, the image was formed between pole and focus. So for both the cases, In the case of convex mirror, for both the cases, we will take the image distance in positive, but in the case of concave mirror, it can be either positive or it can be either negative. Now let's talk about the focal length. So the focus of a concave mirror is at the left side. So that's why in the case of concave mirror, it is negative, but focal of a concave mirror or focus of a convex mirror is at the right side. So that's why it will be taken as positive. It is as simple. So this is the sign convention in the cases of concave and convex mirror. I hope you got it. Let's move on to the next slide. Now, in this slide, we will study about the magnification. It is very easier and very important also, because by the help of magnification, we will find out the nature of the image. The nature of the image. And not only the nature of the image, we will also find out many more things by the help of M. So how to calculate M? It is very easier. First of all, there are two formulas. First formula says that if we have height of image, let's suppose it is h2, and if we also have height of object, then we can simply find out or figure out M. So the formula for finding out M is h2 upon h1. But if we want to figure out M from the other formula, then we have to know the image distance. V is image distance here, image distance, and we also have to know U. We also have to have information about U, and U is object distance here. Object distance. Okay. So these are the formulas to calculate M. Now, if the M is positive, then the image will be virtual and erect. And if the M is negative, then the image is real and inverted. Okay. So we have to remember this. It will be used in numericals. Let's move on to the next slide. If M is greater than 1, then the image is bigger than the object. Okay. Let's suppose if M is 2 or 1.5, then in this case, the image is bigger than the object. But if M is 1, so here the image is same size as of the object. Here the size of the image and the size of the object will same, because we know that M is equals to h2 upon h1, where h2 is image distance. So if M is 1, then h2 will equal to h1. You can cross multiply it here and you can get h2 is equal to h1. Now what if M is less than 1? Then in this case, the image is smaller than the object. Okay. So if M is greater than 1, then the image is bigger than the object. If M is 1, then the image, or you can say the height of the image, is same size as of the object. And if M is less than 1, then the image is smaller than the object. I hope you got my point. Now let's move on to the next slide and let's try to solve a numerical here. It is very important. So guys, here we have been given an object 4 centimeter in size is placed at 25 centimeter in front of a concave mirror of focal length 15. At what distance from the mirror should a screen be placed in order to obtain a sharp image? Okay, find the nature and the size of the image. So it is very simple, because we have to figure out here the image distance where the image is formed, because it is saying that at what distance from the mirror should the screen be placed in order to obtain a sharp image. So where we should place a screen where the image is formed, then only we will be able to obtain a sharp image. So first of all, let's write whatever information we have been given in this question. So we have been given the object size, and that is 4 centimeters. And we also have been given object size denotes h. Object size is written from h, so it is h1. Now let's talk about object distance. So object distance is given 25 centimeter. Now I am doing a mistake. So what is a mistake? You correct me. Let me write one more thing, and that is f, focal length, and it is 15 centimeter. Okay. Now it is your turn to let me know that what mistake I am doing here. Okay. So I have done one mistake, and that is I haven't considered the sign convention here. I haven't put a sign while writing this terms. So what's now you correct me, which sign should I add here? So here we are discussing the case of a concave mirror. So in the case of concave mirror, the object is always placed left side. So that's why here I will be taking minus. Now the focus also of a concave mirror is also at the left side. So that's why the focus is also will be in negative. So this is minus 15 centimeters. Now the height will be positive because it is upright. It is on the upper side of the principal axis. Or you can also understand this by the help of a graph. So in the graph, the positive y-axis or the upper y-axis is taken as positive. So that's why the height will be positive or 4 centimeter. Now let's calculate the image distance. So it is very simple. We know the formula. We know the mirror formula. And that is 1 upon V plus 1 upon U is equals to 1 upon F. Now we have to calculate 1 upon V. So I will send 1 upon U here. It will be 1 upon F minus 1 upon U. And I know that focal length is minus 15 and the object distance is minus 25 and minus will give plus, and that is 25 centimeter. Okay. So now when I solve it, let me take LCM of this, and it will 75. So this will cut 3 times, 5 times, and this will, okay, let me do it 3 times. This will become minus 2.75. And if I inverse it, then it will give me result 75.2. Okay, so this is our image distance. This is our image distance. Let's move on to the next slide. This is solution of this question. Okay, and here also, let's see the solution. So the image distance is V is equals to minus 75 upon 2. Okay, minus 75 upon 2. Now we also have to calculate the nature and the size of the image. So to find out the nature and the size of the image, we have to calculate M. So how can we calculate M? We have a formula minus V upon U, where V is image distance, which we have, and U is object or the distance, which also we already know. So V is minus, this is minus sign, I am writing it here, and V, I will put V value directly from here, and it is 75 upon 2. Okay, and this is the object distance, and in this case the object distance is minus 25. Okay, now this minus and this minus will be multiplied, and this will give positive, and this is minus 75 upon 2 into 25. It will cut 3 times, so it is minus 1.5. Okay, so this is the value of M, minus 1.5. So just by looking at this value, you can easily calculate the information which we need. So first thing is here the m is greater than 1 because you have to leave minus sign for now if you want to calculate the size of the image, because the size of the image will be taken in mode. I think you already know the meaning of the mode. It means here it will always give the positive result. So if you keep this value in this mode, then it will give you 1.5. So 1.5 is greater than 1. So that's why the image is enlarged. Or you can say the image is larger than the object. Now let's talk about the nature. So here the value of m is negative. So if the value of m is negative, so we can go to the previous slide and you can simply see here if the m is negative, then the image is real and inverted. So in this case, because the m is negative, so the image is real and inverted. Okay. So I hope guys you got my point. This was the solution of this question. And now I am ending this lecture and I will see you later lectures. Bye bye.